Alrighty, so we will go ahead and get started. Thank you all for joining us today for our meetup, where we're going to have Toby walk through how to make a programming language. So this is our, I think, second time doing it around lunchtime. So hopefully y'all enjoy this. Just a couple of housekeeping notes before we kind of get started is one, that y'all are going to be on mute, but if you have questions, please submit them via the Q&A. I guess it's a little panel within Zoom. And then also there is the ability to kind of like raise your hand, which Toby may or may not use during the presentation. So if y'all could test out raising your hand, that would be great. Yes, we have one, 2, 3. All right, everybody else is sleeping. Perfect. Very good. Well, in addition to broadcasting on Zoom, we're also streaming on YouTube as well. And the YouTube link we just tweeted out will actually also be the same link to watch the recording of this meetup if you are interested. So with that, I just have a couple slides to kind of go through real quick. Our typical thank yous to our sponsors. So things have changed, right? And they continue to support us. So Saval Group has been great in helping us with the logistics of things, as has Cypress. So Cypress, if you're not testing, you should check out Cypress. If you are testing, you should check out Cypress. If you're testing with Cypress, you should check out some of the new stuff that just launched recently, both on the dashboard and within the test runner. Another big thank you to our organizers who actually make all of this happen. We really could not do this without them. So without further ado, I will stop talking and turn it over to Toby.
Okay, hi everyone. Thanks for coming. I'm gonna share my screen. Let's see if this works.
Yep, we can see your screen.
Can you see my slide? Okay.
That looks good.
Thank you. So let me try to hide this little thing. Okay, so what I'm gonna talk about is first is what does it mean to make a programming language? And what I would like most of you to come away with is a high-level idea of what does it mean to make a programming language, and also to get a feel for what kind of work are the people who implement programming language doing. So the programming languages that you use at work every single day, there's actually people that have created it and are doing ongoing work to maintain it. So I want you to get a feel for what kind of stuff that they are doing. I want to tell you a little bit about some work that I've been doing. I've been really obsessed with learning this craft, and I've created a video series online teaching people how to make programming languages on their own using JavaScript and JavaScript tools. You can find that on my website, tobyhill.com. This series covers parsing and code generation, and it has 19 videos in it at current count. More recently, I've been doing a video series where I make a programming language on stream. So you're also welcome to check that out. That's meant to be a more complete coverage of everything that one might do. Also a little bit about, another thing I've been working on is a post-mortem debugger concept. That's sort of like a research and development idea that I'm working on. If you would like to learn more about that, you can also find it in one of my latest videos where I gave a demo to one of my colleagues. And then I want to talk about my mentoring service. So for the last 3 years or so, I have been primarily focusing my time and making a living by mentoring software developers, and I'm planning on open up those services. So if you're interested in giving more guidance to your developers, you can come here to learn more about that. Okay, so with that, let's talk about programming languages. Okay, so as a software developer, what you're doing most of the time at the end of the day is making programs. And when you're making a programming language, that is no different. At the end of the day, you're also making a program. And a program is a series of instructions that takes some input and generates an output. In the case of when you're making a computer programming language, the input of your program is some code, and then the output of your program is also some code. Now the input is the code that's coming into the input. That's going to be the user code, the code that the users of your programming language are writing or have written, and it should be in the programming language that you're implementing. The code that your program generates is going to be machine code. Now, what is machine code? Well, machine code is code that runs directly on your CPU. And a CPU looks kind of like this. Usually it says Intel on it. And this CPU contains a very large instruction set. And you can actually program it directly using code that it understands. So basically, if you can manage to write a program that can translate the code that the user of your programming language writes into the code that your CPU understands, then you can make a programming language work. And if you do this, then the program that you're making, that is called a compiler. And this particular architecture for programming languages is called compiled programming languages. And there are these widely known and used programming languages that follow this architecture. There's C, C++, Go, Rust, and Haskell for some of the more recent entrants. Okay, so as an example illustration of that, this is a C program. So in order to execute a C program has to go through a C compiler, and a very popular C compiler is called GCC, and GCC stands for GNU C compiler. And the output of GCC at one of the stages anyway is code that looks like this. So this is a close representation of what machine code looks like, although not exactly. The actual machine code just looks like a bunch of ones and zeros, but this is a close representation of it called assembly language, and it gives you a semi-human readable form of what the code you're giving to the CPU actually looks like. And each line contains an instruction that is 3 or 4 characters long. And each instruction takes parameters, operands, and so forth. So for example, an add-L instruction adds 2 numbers together. Move-L instruction moves a value into a particular memory location, and a jump instruction jumps the program from one location of the code to another location in the code. And that's what if statements and while loops use to do their magic. Okay, so far I've talked about compiled programming languages. I do want to mention a few other programming language architectures that exist and are widely used as well. So we'll go through some of those. So another popular one is interpreted programming languages, of which Ruby, Python, JavaScript, and PHP belong to. JavaScript has an asterisk next to it. I'll explain that in a moment. But when you're making an interpreted programming language, then the program you would be writing is called an interpreter. And instead of taking in the code that the user of your language wrote and generating machine code, an interpreter takes in that code and executes it directly. So the end result of the program is actually the result of your code, whether that be it's printing out some output to the console, or perhaps it's generating some DOM elements on a web page. Okay, so another variant or another programming language architecture is transpiled programming languages, and of which TypeScript, Elm, and CoffeeScript belong to. When you're making a transpiler, your program translates code in your programming language to the code in another high-level programming language. But that programming language is not yet machine code, so it cannot directly be consumed by your CPU. And what that means, this code that gets generated is gonna need to go through another program. Program number 2. And that program will either have to interpret I'll call this the target language. So the program number 2 will either have to translate that to machine code, or program number 2 could be an interpreter that interprets this target language and executes it and generates some output. And a popular choice for target languages is JavaScript and C, because those languages are very prevalent and there's just so many developers that know them that they're very popular choices. For JavaScript in particular, it has the added advantage that browsers can execute JavaScript. So if you want to build a web application, well, you don't really have a choice other than to use JavaScript. Well, there's some new choices are coming, but for the historically, that JavaScript has been the only way to build web applications. Okay. Yeah, that's what I'm. In the live coding walkthrough that I'm going to demonstrate, we will be building a transpiled programming language, and it will transpile to JavaScript. I thought that was a good choice because there's there's much less overhead that I would have to cover, because I assume most of you already know JavaScript. And also another thing I would say about transpiled languages is this approach is a quick and easy way for someone who's interested in learning how to do this. This is a quick way to get your hands dirty and make a programming language, because you don't have to learn about how machine code works, which is kind of gnarly. And then finally, there's the bytecode interpreted programming languages, of which Java, C#, and to some extent JavaScript, the modern JavaScript, is built in this way. It wasn't that way in the past for JavaScript, but that all changed when the V8 JavaScript engine came out. They basically put this bytecode interpreted architecture into JavaScript, and then other browser vendors also followed suit after that. So with a bytecode interpreted programming language, what you do is you actually have to write 2 programs. Program number 1 will take the user code program number 1, this one, is a compiler. It will take the user code and generate something called a bytecode. It's an intermediary bytecode, which in spirit, it's kind of like machine code, except that there isn't an actual physical CPU that can execute this bytecode. It's meant to be a architecture independent machine code, or you can think of it as a machine code for a virtual machine. That's another way you can think about it. So it's like machine code, but for a virtual machine is how you can think about it. And the advantage of a virtual machine is that you can implement a virtual machine for any architecture, and then you can use this exact same bytecode then that can work on any architecture. You don't have to write a separate, you don't have to generate different machine code for each architecture. Okay, but once you have bytecode, because that's not enough, you actually need program number 2 that understands the bytecode. That is what the virtual machine is. So you can think of program number 2 as the virtual machine. And the virtual machine is an interpreter. It takes in this bytecode, executes it, and then out come the results. So examples of bytecode, there is the Java bytecode. In .NET C#, I believe that's called the CLR bytecode. And for the browser, there's actually the WebAssembly. But although WebAssembly is a relatively new thing and is not necessarily being used when you execute JavaScript code, but WebAssembly is a recent development. It's a standard that the browser vendors are coming together to create. And what they're basically saying is, we're gonna support WebAssembly in the browser directly. And therefore, if you want to make a programming language and you can translate your code into WebAssembly, then you don't have to write program number 2. We have an interpreter for WebAssembly directly there in the browser. So we'll make your life easier by, you can skip program number 2. You only have to write program number 1. So that's bytecode interpreted programming languages. If anyone has questions at this point, I am happy to answer. And you can use the Q&A to enter questions if you think of one. Okay, so now I'm going to talk about parsers and ASTs briefly before we start the coding demo. Okay, so no matter which one of these architectures you choose, the first step is going to be writing a parser. The parser is what you write to parse and understand the code in your programming language. And the parser outputs something called the AST, which stands for abstract syntax tree. Whoops. And also, when you're building a parser, you're dealing with grammar. You're building up a grammar for your language. So a grammar is always something that's embedded inside of your parser. So before I start, I want to give you an idea of what a grammar is and also what an abstract syntax tree is. So to show you what a grammar is, a really good way to do that is go over to json.org. And I really love this website. This is the original web page for JSON, I believe. And the look and feel of it hasn't changed in probably 20 years. But on the side here, you can see the complete grammar of the JSON language. And the grammar consists of a bunch of rules. They're called production rules, okay? And each production, this is a production rule. Each production rule has a left-hand side and a right-hand side. And what it's saying is I define the thing on the left-hand side as a sequence of things based on the right-hand side, okay? So this is saying, what is a JSON? It's an element. And then if you want to follow that, you can say, okay, what's an element? So an element is down here. An element is some white space, WS, that stands for white space. An element is some white space, then a value, and then some more white space. And then you follow that and you say, okay, now what's a value? Well, value is defined up here. So it says, a value can be any one of these things. It can be an object, an array, a string, a number, true, false, or null. And this is like an or. You can think of this as a value is object or array or. So this is what a grammar is. It sort of spells out in a very succinct way what the grammar of the language is, and therefore what is acceptable in the language, what is valid syntax in the language, and what isn't. Okay. Now, what is it's an abstract syntax tree? A good way to illustrate that is, again, with something you already know. So I'm going to go use this online parsing demo on the sprima.org website. Sprima is a very widely used JavaScript parser that is free and open source. And if you write some JavaScript on the left-hand side, you will get the AST, the abstract syntax tree, on the right-hand side, which represents the code on the left-hand side, okay? So, well, the comment has been ignored. So this large, like very nested object with arrays and stuff inside of it is a description of what this line of syntax is. So it's saying, okay, what is this? Well, it's a program. The top level object is of type program. And a program has got to have a body. And a body is just an array, just a list of statements. And this array has one statement only because it only has one line in it. And that statement has the type of variable declaration. And within this variable declaration, there can be a number of declarations because, as you know, variable declarations, you can use a comma to jam multiple declarations in the same variable declaration. So within variable declaration, there is an array of declarations, but of which there only is one for this example. And I have a variable declarator, and its ID is the name of the variable. And the init is the initial value of that variable. So, and what's the initial value of the variable? Well, it's actually the result of a binary expression, operator being the multiply sign, and the left-hand side of the binary expression is a 6, and the right-hand side is a 7. So this is a very, very detailed and description of the code of the syntax on the left-hand side. And translating the code into this form is what allows your program in the next stage of processing to reason about what the code actually is by going into this tree of objects and making sense of what needs to happen based on this code. Okay, so, all right, let's hurry up and get into it. So the programming language that we're gonna be making is called MyPL because I only have limited time to demo this. It's very, very limited and basic. Basically, it has just enough to implement the Fibonacci sequence and no more. It can add, subtract, multiply, and divide. It can assign some values to variable. It has a while loop, and it can print results. That's it. And it's going to transpile to JavaScript. And this code example basically contains all of the features. Let's get into it. Okay. This is a previous code session that I've recorded, and I'm going to replay it and explain what happens. Okay, so first we're going to npm init to start the project, because this is a JavaScript npm based project. We're going to install a dependency called nearly.js. So nearly.js is is one of the parser generator tools that the JavaScript community provides, and I have tried several of them, and this is one of my favorites. So we're going to be using nearly.js. Also, in my how to make a programming language video series, I will cover how to use nearly.js in detail. Okay, so we've got this dependency in there. Now let's make a grammar file. So we're going to be writing a grammar in the format of nearly.js. We're going to start simple. We're going to say, let's match a number. What is this syntax saying? Is this saying this is a production rule in a grammar, and this is saying I define number to be that. And what is that? This is kind of like regular expression, although not exactly, but you can read it like regular expression. This is a character class, a digit between 0 and 9, and then the plus means one or more occurrences, one or more of 0 to 9. So that's a number. It's an integer. So given that this is a valid grammar already at this point, and we can start trying to do stuff with it. So how do you do stuff with it? Well, you call the nearly C command line tool to compile this grammar, like so, and we're going to tell it to output a JavaScript file called mypl.js. And if you look at the output, this is simply a JavaScript representation is what is in the grammar. And we don't really need to look at what's in here that much. It's not super interesting. It's just a restatement of the grammar in more verbose form, more or less. And once you have this file, then you need to make a, we'll automate or we'll make it more convenient first to rerun this compile step. So we'll put it in as an npm step so that next you can just do npm run gen parser and it'll recompile. Now after you've done that, we need to make a parse script to actually drive the parser. So first you require the generated JavaScript file, and you also require nearly.js, and you plug them together like that to make a parser. This is straight from their getting started page. And once you have a parser, you can start feeding strings into it. I'll do 1 through 3 because that looks like a valid digit. And once you feed a string into it, the parser can have results in it, and we'll print it out. And that parses. It gave a result, which means it parses. If it didn't parse, then it would give you an empty array. Sometimes it can have multiple results, which means there's ambiguity in your grammar. But usually we try to avoid that. Now, if we give it an input that this grammar doesn't understand, such as ABC, it's gonna give you an error like this. Well, I don't understand A because the grammar at present only understands digits. Okay, so we'll put a little bit of like try catch to clean up the error message a little bit. and then we'll move on. Okay, so let's move on to making decimal numbers work. So how can we extend this to support decimal numbers? Well, let's rename this rule to say this is actually digits, not number. And a number can actually be digits followed by a dot, followed by more digits. And if we did that, and now we recompiled the parser and then run it, and now it's able to parse decimal numbers. Okay. Next, as another example, let's parse variable assignments. And for some reason, I decided that variable assignments are done as colon and then equal sign. So so a variable assignment is first an identifier, colon equals, and then a number. And the programming language only supports numbers for now. But what's an identifier? Well, an identifier is some letters, one or more of one of these letters. That's what an identifier is. So at this point, we have the grammar for variable assignments. So let's try it out. So that's actually a mistake. It needs to be a colon. So I'll skip. Okay, so this should work. There's an identifier followed by colon equals followed by a number. So parse succeeded. And now we want to make it so that the program can recognize either numbers at the top level or variable assignments. So what we do is put a top level symbol we call program. And then we're going to say a program can be either a variable assignment or a number. And this initially we're using this arrow to as the operator, but if you have an or, then you use the bar to separate the multiple possibilities, multiple choices. So yeah, a program can either be a variable assignment or a number. But yeah, this will only allow single line programs though, which is very limiting. Later on, we'll fix that. Okay, so now we're gonna actually work on building an AST. I'm gonna skip ahead a little bit due to time constraints. Okay, so we have a very small program. We actually want this. So currently the results that we get is actually this very nested array of strings. So I'm actually gonna show you. So if I do node parse, whoops. Whoa, okay, I actually haven't, okay, I'm not gonna do that, never mind. But if we went back to one of the examples where it parsed, let's see. Yeah, the results that we're printing out here gives you a very, very deeply nested array that it's got string bits within it. And that's not that helpful for what we want to do. We want to convert that into an AST format that looks more or less like what pretty much it generates these objects that have discrete type information in it, so that we can loop through the object or recurse through the object and understand what the syntax is. So how do we do that? I'll show you the end of this section. So the way you do that is by attaching these converters to each rule. Okay, so basically, when the parser is doing its thing, what it's doing is, like, if you had a statement like a colon equals 1, it's gonna take the leaf symbols in your expression and attach them to certain symbols. For example, 1 is gonna be recognized as a digit, which in turn is a digits, which in turn is a number. And then A is going to be recognized as an identifier. And then the combination of an identifier and this symbol plus the number, as this rule says, the combination of those three things will be recognized as a variable assignment. Okay, so given that, what this converter does, which I have written here, and here as these shorthand arrow functions, and these are written in JavaScript, by the way. What these converter functions do at each point, a thing is a symbol is recognized to be another symbol, is it attaches the value that you desire to the symbol. So here I'm saying, oh, a digit, I'm gonna attach the string 1 as this digit. When we combine multiple digits, well, I'm gonna attach all the digits to the digit. And when we get to the number level here, I actually make a conversion. I convert those digits into a number by calling this number function. So here I'm actually attaching an actual number to the number symbol. For identifier, we just attach the string. We just attach the string that represents the identifier to the identifier symbol. And when we finally get to the variable assignment symbol, what we attach to it, the value we attach to it is actually a object with this type discriminator. So we'll say there's gonna be this object called with a type of var assignment and a variable name, which in this case is going to be set to whatever the identifier had, which is A, and it's also going to have a value. And in this case, that's going to be this 1 that was attached to this number. So that's what's happening. This is really hard to read, but that's actually a number. Not a number, that's actually an object literal there. And that's the thing that gets attached to this var assignment symbol, okay? So basically at each level of the grammar, at every production rule within the grammar, we make one of the places that we need to, we make one of these converter functions to tell nearly JS what actual value we want to associate with the symbol. In some cases, in most of the cases where the right-hand side is only one symbol, I use the ID function, which just takes the array of symbols and unboxes it, because it nearly JS packages up all the matching things. Each match on the right-hand side, it packages up the bits into an array. So this data at 0 indexes that guy, and data at 2 indexes that guy, for example. If there's only one thing in the right-hand side, then it still packages it up into an array, and that's kind of silly. So ID just unboxes this value out of this array, is what ID does. And ID is a function that comes out of the box. Okay, let's continue. We're running kind of short on time. I'm gonna skip ahead and do binary expressions. Okay, so at this point we're able to print. We can print an expression. And what's an expression? An expression is either a number, an identifier, and now we want to add the ability to do binary expressions. So binary expressions are like 1 plus 2. That's a binary expression. So now we're adding the ability to do binary expressions. So what does that look like? First, let's separate the unary expression concept from the binary expression concept. unary is there's only one of it. So that's just numbers and identifiers. Then a binary expression, we're gonna say it's an unary expression followed by this underscore. That means optional white space, by the way. We skipped over that, but so it's unary expression, some optional white space, an operator, more optional white space, and another unary expression. So if we did that and we define operator to be one of these things, feeling fancy, so we decided to use the multiplication symbol here. And then we write a converter to represent a binary expression. So we're saying a binary expression is going to be represented as an object with the type of binary expression. And then it's got a left-hand side, an operator, and a right-hand side, which comes from the bits from these matches, right? Okay, so that's what a binary expression looks like. But this will only allow you to do 1 + 1 because both sides are unary. So if you wanted to allow for more complex expressions like 1 + 2 × 3, we actually need to change this so that one of the sides can also be a binary expression. So that's compound expressions. So let's see how to do that. So, okay, if we wanted to parse something like this, then we'll say, oh, actually on the right-hand side, that can also be an expression, which in turn can either be unary or binary. So now that's going to allow for these nested binary expressions. Okay. All right. I'm gonna skip ahead because we're running low on time to where we're actually generating code. Okay. So at this point, we actually have given a program that looks like this. We run the parse program, and it will actually generate a file that ends in .ast. So if you parse this program, you're gonna end up with an AST file that looks like this. And this is in JSON format, the AST of that program. It's a very detailed description of what this program is, right? So now once you get to this point, you have a parser. You have a parser that works. Remember you have code goes into a parser. It's got some grammars in it. And that will spit out an AST for you. And the AST, that's what we're looking at right now. The next step after you have this to make a programming language work is take this AST and put it through another program, another sub program. It's called the generator. And you have it spit out the target language. In our case, that is JavaScript. Okay, so that's what we're gonna do. We're gonna write a program. I'm gonna call it generate, and it's gonna JavaScript that represents this AST. It represents what this AST is actually trying to represent. Okay, let's go ahead and do that. We'll write a script. I like to use async await with Node.js. It's really enjoyable way to write code for me. So I'm going to read in an AST file, a .ast file, and then we're going to sort of infer the output JavaScript file. So for now, we'll have this generate JS function just return a console, just print out hello world. Okay, we'll write that out. And if we run this code now, it generates example1.js, which looks like that, and it'll print out hello world. Okay, fine, but it doesn't do what the program is actually supposed to do. So how do we do that? Well, let's actually loop through this AST structure. This AST has an array of objects, each object representing a statement in the program, right? So we can write a loop to go over that. So we know the statements coming from the AST file. After we read in the file, and then we did JSON.parse to get it back to the JavaScript structure. We can loop through that array and then go through each statement object. And then we can say, if that statement happens to be a variable assignment, then we're gonna make a line of JavaScript that is a variable assignment. And I'll do this side by side. Yeah, so, and I can get the variable name from here, and I can get the initial value from here. And we can just format that as a line of JavaScript. And then I'll append it to this array of lines. And at the end, I'm gonna join those lines back together. Now we have a JavaScript program. So generate JavaScript based on this AST file. And now we have a JavaScript file, example1.js. It looks like this. This actually looks like valid JavaScript, right? So now we're cooking. How do we generate JavaScript for binary expressions? If we have a binary expression like this, m plus n, how do we generate the equivalent JavaScript for that? Okay. We can use recursion, and this can be nested too. That could be compound expressions. So we can use recursion for that. So we're gonna make another function. We're gonna call it generate a JavaScript expression, generate JS for a particular expression. An expression is like a statement that will evaluate and give you a value. So a binary expression is that, or just a single number literal is also that, right? So we'll make a function that will just knows how to convert expressions into the JavaScript version of the expression. And if in case it's an object, we know that we need to look at the type. But if it's not an object, we know it's either an identifier or a number, because in the setup that I have, an identifier is simply a string in the AST, and a number is simply a number in the AST. And in those cases, we can return them as is, and it'll sort of concatenate with strings correctly. But if it's not one of those things, we actually want to look at what type the object has. In particular, if the type of the object is a binary expression, we actually need to go into its left-hand side and right-hand side and figure out the details about that binary expression. So how do we do that? Recursion. We need to recursively call ourselves to convert our left-hand side to a JavaScript expression and convert the right-hand side to a JavaScript expression, because either the left-hand side or right-hand side could be yet another binary expression. So we use recursion to first have that object go through the generate JS for expression function. And then it's going to do the same to the left-hand side. In this case, well, just a string, so it'll go into the else case and return. But for the right-hand side, it'll actually have to go through this clause yet again to do its left-hand side and right-hand side. So that's here and here. And then once the JavaScript expression for that is calculated, it goes back up to the parent object, and the parent object combines them together. So that's what's going to happen. So we're going to say, okay, we format this line as JavaScript. It's going to be the JavaScript version of the expression, and then the operator, and then oopsies, and then the JavaScript version of the right-hand side of the statement. Okay, so we generate that file, generate the JavaScript version of the program now. And we get this, but the multiplication symbol is not a valid JavaScript symbol, so that's a problem. How do we fix that? Well, let's make a map, an operator map, to translate the operators, right? And then that's not too hard. We'll just look up that operator map to translate the operators in MyPL to the operators to JavaScript. And let's look at that. And that works. That actually looks like a working JavaScript program. Let's see. Let's do console.logs. So we have print statements in this language. And if we parse this file, we'll get the AST looking like this. The AST for a print statement looks like this. There's a type is print statement, and there's an expression to be printed, right? So how do we get that to translate to JavaScript? Well, you know how to print things out in JavaScript. We just get the expression, convert it into the JavaScript expression, and stick it into a console.log. Let's generate a JavaScript program for that. And now we have some console.logs printing stuff out. Okay. Let's do while loops. Why not? Let's do while loops. Okay, so we have, let's see. Let's write a while loop. So expression, AST for a while loop. What does it look like? Do we have it? Yeah, AST for a while loop looks like this. So the type of the object is a while loop. There's a condition, which is an expression, but we already have a function that can convert expressions, so not a problem. And then while in it, and we already know how to deal with about an array of statements. That's also not a problem. So this should be okay. We can do this, right? So we take the condition of the while loop, convert it into a JavaScript, take the body of the state of the while loop, convert it to a JavaScript as well. I can recursively call myself to do this one, because generate.js at the top level is already a function that takes an array of statements and converts it into JavaScript. So it can just reuse that. And now we format a while loop that's a valid while loop syntax in JavaScript. And now it writes it converted into JavaScript. Let's see what it looks like. Yeah, and that looks like it kind of works. There's probably a small problem in there, but we're gonna fix it. So let me see. Well, let me go back. Yeah. Okay. Yeah. So basically, at this point, we're at the point of where we can make a little program like this that has a while loop and a loop counter, and it can translate it into JavaScript correctly, and then we can actually run that JavaScript program, and it works, right? Okay. So finally, one last thing. So first, we made a convenience script called run.js, which will do both the parsing step and the generating the JavaScript program and execute the program using Node.js to speed up this workflow. And now let's attempt to write a Fibonacci sequence program in MyPL. Okay, so we only have while loops. Okay, so you gotta make do with what you got. So we're gonna try to loop n times, whatever n is that you want to go up to. You want the nth number in the Fibonacci, we'll say 10. We're gonna have a variable fi to represent the current number, and the fii will say that represents the next number. And then we'll do this add the two numbers and swap them strategy so that, yeah, I'll show you. So we'll loop. I'm gonna print out the current number in the sequence. I'm gonna add the two numbers and then swap them, right? So the temp is gonna be the new value of FII. So the temp is gonna be the new next value. And then the FII is going to the current value. The current next value is becoming the current value, right? And there it is. And I think I forgot to increment the loop counter, so it went into an infinite loop. So let's fix that. And after that fix, it worked. So we've written a Fibonacci sequence program in a brand new programming language that we made. Yeah, so that's the end of the demo. I guess we're pretty short on time, but I don't know. Let's see. I'm not sure if we have questions or not, but I thank everyone for watching this.
I don't see any questions.
Okay.
However, if somebody wants to raise their hand and ask one verbally, we can unmute.
Okay. Yeah, if anyone has a question, I can try to answer it. But thank you everyone for attending and learning about. Oh, and I guess I'll just reiterate, if this was interesting to you, if you feel like motivated to learn how to do this yourself, go to tobyhill.com. I have this video series going into more details about how to do this.
Awesome. Great. Well, thank you so much, Toby. We've got just a couple of closing slides here, which I'll run through real quickly. So we always like to promote community events. So we've got a couple here. It looks like Refactor Tech. The new dates for it are August 12th through the 14th, and we've got a promo code there to get you $50 off. Next, we've got Render ATL, currently scheduled for August 24th through the 26th. You can visit their website for additional information as well as tickets. And then some meetups worth checking out. We've got React and Angular. And then there's one other conference that's kind of in the planning stages still, and that is Drupal Camp. They do a lot of decoupled Drupal talks. So a lot of folks are using JavaScript frameworks as a front end for Drupal being the back end. We have a couple of our sponsors are hiring. Both Savant Group is. You can visit their career site, as well as Cypress. And at Cypress, I know that we are definitely hiring for a technical account manager and account executive. So if that sounds appealing, definitely check it out and apply. If you have opportunities to share with our community, or if you're looking for a job yourself, definitely check out our job board with the bit.ly link right there. And then do follow us. So we tweet out the link to watch this live. And then we also have a YouTube channel where you can view our previous talks, as well as, live recordings, or rather live broadcasts of these virtual talks as they happen. And then if you're interested in speaking and you want someone to kind of give you some constructive feedback, Rachel is offering to do that. So you can shoot her an email. She'd be more than glad to help. And then I will close with my absolute favorite slide. A candle loses nothing by lighting another candle. This is so true. Toby's nothing less. Everyone on the presentation is something more. So really just get involved and kind of help other folks. So if you're interested, feel free to shoot us an email or reach out to myself or any of the other organizers on Twitter. Thank you all so much for coming out, and we look forward to seeing you again next month, likely also virtual. Take care. Bye.
Thank you, everyone.